Welcome back to Java Internals Crashcasts. I'm your host Sheila, and today we're continuing our deep dive into the fork-join framework. In our previous episode, we explored the fork-join pool, and now we're moving on to two crucial components of this framework, RecursiveTask and RecursiveAction. Victor, are you ready to help our listeners understand these concepts?
Absolutely, Sheila. I'm excited to delve into RecursiveTask and RecursiveAction. These classes are fundamental to writing efficient parallel algorithms using the fork-join framework.
Great. Before we jump in, let's start with a quiz question for our listeners. Here's the question. What's the key difference between RecursiveTask and RecursiveAction in terms of their return types? Think about it, and we'll reveal the answer at the end of the episode.
That's an excellent question, Sheila. It touches on a fundamental aspect of these classes that developers need to understand when choosing between them. I'm looking forward to discussing this in detail as we explore the topic.
Perfect. Let's begin by explaining what RecursiveTask and RecursiveAction are. Victor, can you give us a high-level overview?
Certainly. Both RecursiveTask and RecursiveAction are abstract classes that extend fork-join task. They're designed to be used with the fork-join pool we discussed in our previous episode. The main purpose of these classes is to allow developers to implement divide-and-conquer algorithms that can be executed in parallel.
That's interesting. So how do they differ from each other?
The key difference lies in their return types. RecursiveTask is designed for computations that produce a result, while RecursiveAction is for computations that don't return a value. Think of RecursiveTask as a worker who completes a task and brings back a result, while RecursiveAction is like a worker who completes a task without needing to report back with a specific value.
That's a helpful analogy. Can you elaborate on how we implement these classes?
Of course, for both classes, you need to override what's called the compute method. In RecursiveTask, this method returns a result of the type you specify when extending the class. For RecursiveAction, the compute method doesn't return anything. The compute method is where you implement your divide-and-conquer logic.
I see. So, within the compute method, we would check if the task is small enough to compute directly, and if not, we'd split it into smaller subtasks, right?
Exactly. This is a crucial part of implementing these classes effectively. You typically follow this pattern. First, check if the task is small enough to compute sequentially. If it's too large, split it into smaller subtasks. Then invoke these subtasks using what's called the fork method. Finally, join the results for RecursiveTask, or wait for completion for RecursiveAction. This approach allows the fork-join pool to efficiently distribute work across multiple threads.
That makes sense. Can you give us a real-world example of when you might use RecursiveTask versus RecursiveAction?
Certainly. Let's say you're processing a large array of numbers. If you want to compute the sum of all numbers, you'd use RecursiveTask because you need to return the sum. On the other hand, if you're updating each element of the array in place, like multiplying each number by 2, you'd use RecursiveAction because you don't need to return a value. You're modifying the array directly.
That's very clear. Thank you. Now, what are some common pitfalls developers should be aware of when using these classes?
Great question. One common mistake is not choosing the right threshold for splitting tasks. If you set it too low, you'll create too many small tasks, which can lead to overhead. Set it too high, and you won't fully utilize the available parallelism. Another pitfall is forgetting to call the join method on forked tasks in RecursiveTask implementations. This can lead to incorrect results or tasks not being completed. Lastly, be cautious about shared mutable state. These tasks run concurrently, so you need to ensure thread safety if you're modifying shared data.
Those are important points to keep in mind. Do you have any tips for optimizing the performance of RecursiveTask and RecursiveAction implementations?
Absolutely. Here are a few tips. First, choose an appropriate threshold for task splitting. This often requires experimentation to find the sweet spot for your specific use case. Second, try to make your tasks independent to minimize contention and maximize parallelism. Third, use the invoke all method when you have multiple subtasks to fork and join. as it's more efficient than calling fork and join separately. Finally, for recursive task, consider using compute directly for the last level of recursion instead of forking a new task, which can reduce overhead.
Those are excellent tips, Victor. Now, before we wrap up, let's reveal the answer to our quiz question. The key difference between recursive task and recursive action in terms of their return types is that recursive task returns a value, while recursive action doesn't return anything.
That's correct, Sheila. Understanding this difference is crucial for choosing the right class for your specific use case.
Thank you, Victor, for this informative discussion on recursive task and recursive action. To summarize the main points for our listeners: 1. Recursive task and recursive action are key components of the fork-on-join framework. 2. Recursive task is used for computations that return a result, while recursive action is for computations without a return value. 3. Both classes require implementing the compute method, where you define your divide and conquer logic. 4. Proper task splitting and handling of subtasks are crucial for effective implementation. 5. Be aware of common pitfalls like incorrect thresholds and shared mutable state. In our next episode, we'll be exploring concurrent design patterns, starting with the producer-consumer pattern. Don't forget to subscribe to Java Internals Crashcasts and leave us a rating if you're enjoying the series. Thanks for listening.